chapter. Here we go.
It's ready. Yeah. Let me get on my microphone.
Hello, everyone. I'm Xinhai Jiang, working with Matthew Foster. I will present our recent work on the enhancement of superconductivity due to the spectrum-wide multifractal wave functions. We studied the mean-field theory of the S-wave superconductivity of two models, the Aubrey-Andre model and the polar random banded matrix model. The wave function, all the wave functions of both models are multifractal at the metal insulator transition, and the Aubrey-Andre model have the additional feature of flat bands. Here we show the plot of the order parameter and the phase diagram of the two models. The white curve gives the largest superconductivity order parameter, and the red curve indicates the metal insulator transition. We can see that the two curves are almost exactly the same for weak interactions, and the similarity of the results in these two models indicates that the superconductivity is indeed due to the enhanced due to the multifractal wave functions. Please come to my poster for further information.
Hi. So are there Majorana fermion in P-wave superconducting wires? So the Kitaev model is a mean field model which does not conserve the number of particles. And there is one decoupled Dirac fermion. And when you add this zero energy fermion to the even parity condensate, you get the odd parity condensate and vice versa. And this fermion decoupled to two isolated Majorana. So beyond the mean field, the interacting Hamiltonian conserves the number of electrons. And then the even condensate is a electron pair correlated condensate. The odd condensate, the ground state with the odd number of fermions is a pair correlated whole state. And there is no linear combination of original fermion which can transfer between these two vacuums. You have to reconstruct the whole ground state to go to the other one. And so there is no Majorana fermion. Thank you.
Yeah, so our work is basically using neutron scattering to study how the lattice is involved in the recently discovered vanadium-based cadmium superconductors, the 1353. So using elastic neutron scattering, basically we have found the static lattice distortion corresponding to the 2x2 superlattice below CW transition temperature. And also, when we're using inelastic neutron scattering, we have found a pronounced boson hardening at the CDW wave factor below CW transition temperature. So, in contrast to the previously proposed a priori electronic origin of the CW order, our results suggest that the electron-boson coupling plays an important role in the CW order of the 135 family.
So hi everyone, I'm Yimi Wang from Rice, and my work is about the quantum criticality of Canon lattice model. So this work is motivated by a recent experiment on frustrated heavy fermion metal, silver and palladium, aluminum, and we began to investigate the transition from the antiferromagnetic states to the paramagnetic states with small Fermi surface, which is a frustration-driven transition. And the method we use is the renormalization group technique to investigate the single model in the presence of the counter coupling. And the result we find is that the counter coupling is marginal inside the AFM phase, and it is irrelevant at the quantum point between the AFM and the PS state. For further details, welcome to see my poster. Thank you.
Hello, everyone. I'm a new postdoc in Alan McDonald's group at UT Austin. And on my poster, I will present some results on spontaneous valley coherence in twisted bilayer graphene, as shown there on the left, encapsulated by ferromagnetic insulators, shown right next to it. Remarkably, this system can have flat bands that are degenerate in valley, but non-degenerate in all other degrees of freedom. This makes valley-valley interactions become extremely important and can lead to non-trivial valley mixed states, as depicted with these cute arrows there. Yeah, so we find such a state in the system, and we explain it in terms of some effective valley-valley interactions. So please stop by if you're interested to discuss it.
So hello everyone, I'm Lei Chen from Rice University. My poster is basically a continuation of Professor Chimiao's talk yesterday. And we know that the strong correlation is gonna drive emergent low energy excitations. And also we know that the space groups gonna constrain the topology or classify the band structure of the band structure in a non-interacting system. And we would like to propose that these crystalline symmetries also classify the low the band structure of the low energy excitations, and we verify these principles in the square net lattice and find other normal types of nodal structures. And if you want to know more details about these things, please come to my poster lot, and we can have more discussions.
Hello, everyone. I'm Hao Yu from Rice University. So the topic of this slide is unconventional superconductivity from the Fermi surface fluctuations. Here, we basically focus on these heavy Fermi metals that can provide prototypes, citing to study these quantum criticalities. And in many of these quantum critical heavy Fermi systems, there is superconductivities with a high TC, where the transition temperature reaches several percent of these effective Fermi energies. And in addition, in various materials, there is a large to Fermi surface jump at this antiferromagnetic quantum transition point. Here we can study this model from a theoretical perspective, where address how such a high TC superconductivity can develop from this Fermi surface jump, or in other words, from the large to small Fermi surface fluctuations. And here is our theoretical phase diagram, where we can see there is a broad superconductivity region appears near this quantum critical point. So more details are in the poster. So thank you.
Hi, my name is Rolf from the University of Houston. In this work, we derive conditions for which Majorana fermions can be found in the superconductor vortex core of a wild semimetal. There have been several platforms to realize Majorana fermions, such as the semiconductor, superconductor heterostructures, and the topological insulator and the topological banded insulator. However, the wild semimetal platforms has been less explored. So in this work, we show the condition for which we can find surface or chiral Majorana fermions, namely that it's such that it depends on the Fermi arc structure, the proximity of the wild nodes, the net chirality and the vortex orientation. And we predict a gap vortex if the net chirality in each KZ plane is 0. Otherwise, we predict a gapless vortex if the net chirality in each KZ plane is non-zero. In either case, we can have surface or chiral Majorana fermions emerging either at the surface or the bulk of the superconductor. Thank you.
Hello, this is Chen from Rice University, working at Professor Ming's group. So basically, this is a combination of two pieces of work. So the first part is our direct observation of Dirac fermions, clean Dirac fermions near Fermi level in this strong gallium-2 and barium gallium-2 system, where these Dirac fermions, they are the 3D analog of the Dirac fermions in graphene, and they also form the SOC split Dirac nodal lines along the outer direction. And also beyond these Dirac or wire fermions, solid state system can also support higher order unconventional fermion like 3-fold, 4-fold, 6-fold, or 8-fold in lattice system. And we use angle resolved photon emission spectroscopy to study charge density wave compound in tantalum telluride 4, where we directly observe the charge density wave for the electron pockets near Fermi level. And theory also suggests that there is 8-fold fermion at the A point and also double hourglass fermion around the around high symmetry direction. If you want to know more details about the experimental results of these two systems, you can come by my poster session.
Hi, I'm Jianwei Huang, also from Ming's group. So my poster is about revealing these multiple topological bands in this European gallium-2 aluminum material. So this material is this crystal structure is this bicenteral tetrahedral, which is the same as the more famous 122 iron-based superconductors. We find that there is a 3-dimensional bulk Dirac point which is at Fermi level, and this protected by this C4V axis. We also find these are these so-called jump height surface states, which inside this bulk Dirac Lodo loop, and this bulk Dirac Lodo loop is protected by this 001 mirror symmetry. We also find this novel surface state that smoothly evolve around this Brilliant zoom, and we find that the interesting about this surface state, we find that part of it along this gamma X direction connect this n-2 and n-1 bulk band, and part of it along this gamma n direction connect this n+1 and n+2 bulk band. These surfaces should be topological non-trivial, as it always connect these n and n+1 bulk bands. This material also has the charge density weight and the magnetic order, so this will be a good system to study the interplays between these orders and the topology. So if you're interested, you can talk to me in the poster session. Thank you.